Hey guys. Oh, hold on a second here. Turn off my space heater. Uh, this week we are going to be talking about categorical or nominal independent variables. We have kind of covered this a little bit in the past, and I want to just talk a little bit more about this in detail. You know, in the past we've talked about using our G minus one to come up with what we call code variables. Remember that when we're talking about coding variables or categorical variables, what we're really talking about is a set of independent variables that represent some sort of grouping. In a second here, I'm going to show an image that I think kind of highlights that a little bit more. Um, what I want you to remember, what I want you to think about here is that each one of these independent variables gives us specific information about a group relative to some other piece of the data. In some instances, that piece of the data is the mean of the group. In some instances, the piece of the data is the intercept of some comparative group. And in fact, with all of them, regardless, once you have your coding scheme in, what you do find is that regardless of the coding scheme, your F statistic and your R squared are going to remain constant throughout. Let's take a first dive here into dummy coding. Now, if you recall in the past, we've talked about dummy coding. And when we do dummy coding, we are coding groups for G minus, or coding independent variables for G minus one group. In the example over here, we have four different groups. We have some sort of value for the dependent variable. And then we create these dummy coded groups. And notice that we have dummy coded groups that are all one, which indicates group one, all ones for D2 to indicate group 2, all ones for D3 to indicate group 3, and then D4 we don't have a dummy coded group for them. They are the always zero group. In other words, they are the comparison group. So when you run your regression model, you will only have D1, D2, and D3 in there because D4 in this instance is the always zero group, and it becomes the comparison group, and everything else is relative to D4. And so just looking at this, and you can see these values, you can kind of guess that we're going to have, based on this, an intercept of, if you had to guess, you don't even have to guess because the intercept is going to be the mean of this group, and in this case it's 40. And then each one of these slopes, the slope for D1, for D2, for D3, will be some sort of negative coefficient. In this case, I can see, so we have 5, 4, 6, 5. The average here is obviously 5, which means if this average is 10, then the coefficient for D1 would be minus 5. And then based on the variability, the pooled kind of variance here, you would be able to calculate some sort of standard error for that. But we can calculate very easily what each one of these intercepts or slopes would be for each one of these groups. If you then want to change it up and make a different group, the comparator group, you would have a D4 category over here that would be all ones along here and then zeros for everything else. And recall that you can't have all four categories in at once. You can only have three categories in at once. And what happens when you add in D4 is you just wind up flipping some coefficients because depending on whatever group then becomes a zero group, you would have that as your always zero reference. So for example, if we wanted to make group 3 our reference group, we would have D1, D2, and the D4 that we created, because then D3 would be excluded. You would have no ones for D3. You would have zeros, zeros, and again in D4, more zeros. This will give you actually the exact same f that you would get from calculating a one-way ANOVA. And from these values and the n here, you can actually calculate your sums of squares and everything that you would get from a traditional ANOVA, but you don't have to do that. They are the exact same type of test. A cautionary tale when you are doing dummy coding. A lot of times you'll see people that will code men as 1 and women as 2, or some other type of coding system like this, right? When you do this, if you were to do this, bear in mind that there is no zero group here, and there is some sort of hypothetical zero group out there. And if you entered this in as a predictor, then the intercept would actually be what would be considered a zero group here, and there isn't a zero group, so it would be some number that has no true value because there's no actual zero, but it would mathematically assume that there is a zero, and you would get 0 for that. You would get some illusory number that's not true. So when you're coding, make sure that your codes are 1s and 0s or something along those lines, something kind of consistent with that. At least for dummy coding, there is another type of coding that we're going to talk about today, and that is unweighted coding. So I say unweighted because we are not accounting for the fact that there might be different numbers of people in each group. So we're still going to have g minus 1 coded variables, but we might decide that we actually want to compare this to the true mean within the data set, right? And if that's the case, then you would do something along these lines. You still have to have a comparison group, but that comparison group is set as -1, and the other group in there is going to be set as 1. And then everything else will be set as 0. So notice with this coding, you would actually, if we were really interested in just lower white collar workers as an occupation category, we would have a 1 right here and a 0 here, and then zeros the rest of the way down. Similarly, if we were interested in skilled, we would have a 1 here and then 0 here and zeros the rest of the way down, but keeping that 1. But in this case, we don't. We set this -1 here, and this will actually zero out the entire group and produce a relative effect of this group or this group or this group, based on which coding effects are in there, relative to the mean of the entire, across all groups, the entire mean. However, this and this will only be equivalent to the true mean if all of the groups are equal, because this would have to add up to 0 and this would have to add up to 0. And if they don't add up to 0 within the coded condition, then you don't actually get the true mean across all of the comparisons. This is why it's called unweighted. The next thing that we're going to do is actually weighting the variables. So in this case, you'll still have g minus 1 coded variables. However, it solves the issue of mean comparison. Now we're going to look at this in class, and I'll show you that when the groups are close in size, then you wind up getting an intercept that's fairly close to the total mean, but not exact unless all of the groups are the exact same size. However, weighted coding allows you to reflect the relative difference in sample size or in group size across conditions. And the intercept in this case actually does become the true mean. Also, in the unweighted condition, each one of the predictors that you enter, E1, E2, E3, E4, E5, wind up becoming the relative difference of this group to the average within. This is an unweighted average, right? In this case, for weighted coding, you will have an intercept that is the actual true mean, and each one of your contrast coded or your weighted coding variables, your independent variables, your g minus 1 coded variables, is the difference between that group and the mean of the entire group. There are a number of different reasons that you might want to do this. Perhaps you don't actually have a true control group. Perhaps you have a bunch of different groups. You might have age categories and test scores, and you want to look and see if age categories vary, if test scores vary by age category or something along those lines. The way that you do this is you say that you have each one of your codings, at least for that very first kind of comparator group, and it's not a true comparator group, remember, is going to be the n of your group for whatever group it is, divided by the n of your comparator group. Doesn't make a ton of sense when I say it out loud. There's a description of it on page 329 of your text. But more importantly is that we will go ahead and do this in class, and we will walk through this so that you can see how exactly weighted, unweighted, and dummy-coded coding works. There are two other types of coding. We're not going to go through them. They become increasingly more complicated. One is called contrast coding, and contrast coding is nice when you have some sort of a priori hypothesis about the effects of a group relative to another group and relative to a control condition. We will not worry about that now. Most of the time, we are only necessarily worried about the differences relative to some sort of control. But there are times when you might have a control, a treatment 1, and a treatment 2, and you want to know, is there a difference between treatment 1 and treatment 2, and is there a difference between treatment 1 and treatment 2 and control? You can get that using a simple flip-flop of dummy coding, but also you can do this through contrast coding where you never actually have to do any type of flip-flopping. But that is it for today. Nice and short. I actually expect class will also be nice and short this week, which will give you guys a little bit more time to finish up your final exam or your midterm exam. Have a good day, and I will see you guys on Thursday.